So I'm testing the lens braking reaction by shorting out one of the three phases of this motor here with the permanent magnet rotor that has magnets slanted at 32 degrees, 35 degrees. So here's the three phases, 1, 2, 3, coming out of here. And I'm just going to short them out, short one out, and see what happens to the draw over here. This is the prime mover. This is another rotoverter motor. This just has a standard rotor in it like that. Has ceramic bearings in it too. It's very low draw motor. So while it has the load of spinning this, just spinning it, it's drawing between 30 and 40 milliamps with my ammeter and 20 amps AC. And I have a 4 UF run cap. And I tried some other run cap sizes, but this is the best one. It's going between 30 and 40, so say 35 milliamps. Now, when I short this, just one of these phases out, I get, it should go up to 110 milliamps. Okay, that one of these phases is shorted out. The back EMF is making a lens reaction, lens braking reaction, and it's making the draw go up to 110 milliamps. If I take it off, it goes back to 30 and 40, okay? Now what I'm going to do is take this motor and spin it around so this shaft is being turned by the prime mover of this motor. This is drawing 120 volts right from the grid, the prime mover. Okay, so that's the next test I'll do. Hold on and I will flip this motor around, come back. The thing is these magnets are sloped at 35 degrees when it whirls past the laminates inside here. So there's kind of a high edge to the magnet and a low edge to the magnet as it whips past. Now I'm wondering if it's better to have the high edge hit first or the low edge hit first, or does it even matter at all? And so I'm going to flip the rotation of this around by flipping this motor over, and then we'll see if we get the same numbers or different. Okay, so hold on. Okay, now I got it spun around. This motor's now going in the opposite rotation, this generator, this motor working as a generator. And with nothing shorted out of the phases, it's the same draw. It's actually a little less going this way. Before it was flashing up to 0.04. So there does seem to be maybe an advantage of the rotor of those permanent magnets in there spinning the direction it is now. I'd say so. And now I'm going to short out this to here. Shorted. And it goes up to 110 milliamps, just like the other one. When it was rotating the other way. So there seems to be a slight advantage turning the direction it is now, but when you put it under load you can't really tell anything different. Okay, there's that test. Now what I'm going to do is I'm going to use this motor as a pony motor, just as it is now. This is going 1750 RPM, so is this. And that's the sine wave, 60 hertz sine wave speed that it'll run on, AC. So now I'm going to power this as a motor and use this to get it up to speed, because I couldn't get this to rotate with a start cap like you do with this one at startup from stop. You know, like a regular rotoverter, you use a start cap, you get it up to speed, then you go to a run cap with much lower value. So I have 4 UF on this right now. I tried other values, but this gives the lowest draw. It's pretty consistent down at 30 milliamps right now. So now I'm going to power this. I'm going to run both motors, this one and this one, from the AC power. And I did this before and I found a 35 UF cap as the run cap for this. Lowered the draw a little bit. I need to run through a lot of run cap values on this one. Also, before I experienced it getting hot, however, I had these 2 magnets stuck to the frame, very strong. Maybe it magnetized the laminates, caused the heat. I don't know. So I'm going to do this again. And now we're going to watch this work as an AC motor now. Before I had 2.1 amp draw going into this, and this one disconnected, so this one was just a load at that point. And that's too much amps, way too much amps. But maybe I can get that down lower with different run cap values here. And so I'm going to put this on pause again and come back to when both of these motors are powered by 60 hertz AC, 120 volts. And then I'm going to disconnect the power to here and watch this work as a AC motor running on 60 hertz, 120 volts. Again, I have only 2 magnets in that rotor. It's a rotor like this, and there's just like one here and one here. This is blank and blank. That's what's in there right now. Here's the 2 magnets I pulled out. So, put you on pause, come back when I got it going. Okay, now I've hooked the ammeter from L1 coming in the 2 AC lines of the input coming in, and I hooked from L1 over to L1 over here. I've done this before, and this will make the motor go in the same direction as this one, because if you're going in the opposite direction when you try to have them at the same time, have the same power, it's not going to work very well. So, okay, so that's the first step. Hold on. Now I have this motor to be running as a motor. In fact, it is right now. We have power going into this rotor motor and power going into this rotor motor. This has a 35 UF run cap across L3 and L2. And then L1 goes to L1 here, and L2 goes to L2 here. So, when I disconnect this white wire, this motor will be disconnected, this one will be connected, this will now be the load of this, just spinning it through the shaft, and this will tell you how much amps and 120 volts is feeding this motor now. And here we go. It's dying down. One moment. Okay, just a bad connection on this clip. So anyway, so now this is not connected. This motor is not connected. Look how much amps this draws now. And I do have a 35 UF run cap. This is in rotor mode now, running on single phase, AC, 120 volts, 60 hertz. So it does work as a motor running on an AC signal with 60 hertz, but you have to use a Tony motor to get it up to speed first. So this is about 240 watts, which is ridiculous, but I don't feel any heat coming from it right now. Okay, now I'm going to put you on pause again, and I'm going to go through some run cap sizes here for this motor, which is now running off the power. And see if I can get the draw down below 2 or anything but that. Okay, so hold on a bit. Okay, I settled on 45 UF cap after going through some caps over here on the run caps from L2 to L3. And look, I got it down to just below 2 milliamps, 200 milliamps. And if I do not have a run cap, it goes up to 2.6. So the run cap, so I helped a little bit, but you know what? I feel heat here. So what I want to do now is see what the voltage is across this run cap and see what the current is circulating in this run cap in this motor with the permanent magnet slanted at 35 degrees. So I'm going to do that and let you know what happened. Okay, hold on. Okay, the voltage in AC across the run cap, the 45 UF run cap of the permanent magnet rotoverter, PMRV I call it, is that much, 89, 88 volts. Not such high voltage considering that there's 120 volts coming into it, but let's see what the current is. I bet you the current's pretty big. Hold on. Current is not so great. 610 milliamps. Considering there's 2 amps going into it, so it's not looking too good for the run cap phase right now. One moment, I'm going to take off the run cap. It's kind of weird. It says the voltage is now 37. So hooking an ammeter in series to check the circulating current knocks down the voltage. So one moment. Okay, I got the current circulating in the run cap phase with a 10 UF run cap to be 160 milliamps AC. However, it's getting hot. So my curiosity is satisfied that the way I have those magnets right now is not going to be practical because it's getting hot. So I'm going to call this test off. This is good enough for now. I'm probably going to put a new rotor in it, maybe with smaller magnets. I should probably try four magnets instead of 2, the original plan. But it's getting kind of hot. Too much current going in there. Okay, thanks for watching.